So, good afternoon, everybody. Welcome to this webinar. This webinar, Arctic 6G webinar, exploring future 6G opportunities. It's becoming a kind of a tradition where we present every November. We present our results that we have in several regional projects across Sweden and Finland in the north in the Nordic region. And so I think this is the third or the fourth year we do this. We have 5 interesting presentations, and we will have we will see some interesting results in the coming 1.5 hours. So my name is Jaap van der Beek, and this is organized by the main organizer of this webinar is the Interreg Aurora project, Arctic 6G. So this will proceed as follows. We have, like I said, 5 presentations, and we have a Q&A buttons in this webinar. So I would invite you, if you have any questions during the presentation, to put them in the Q&A, and we will take them right after each presentation, as long as our time permits that. So roughly we will have 15 minutes per presentation and an additional few minutes of questions, if any. So with that, I think we are ready to listen to the first presentation. You see the agenda for today, and the first presentation will be given by a PhD student from Luleå University and Amirreza Moradi. So I invite Amirreza Moradi to switch on your video, your mic, and I will unshare this. I will unshare my. I will stop sharing here, and so go ahead. You can share your presentation, and please, floor is yours.
Thank you.
So yes, we can see we can nicely see your presentation. So please go ahead.
All right. Yeah. All right. Thank you. Good afternoon, everybody. I'm Amirreza, PhD student in signal processing at LTU, and today I will talk about cellular coverage inequality. With increasing dependency to cellular networks, there are still people, or there are still areas that do not access to cellular networks. The gap between areas or individuals with access to reliable cellular coverage and those without access to that, called cellular coverage inequality. And it can be due to many reasons, like it could be due to lack of infrastructure. It can have something to do with the attitude of the people, or it can have something to do with the income, education of the people, or it can have some reason due to the geographical aspects, like rural areas or remote areas. If we want to have a look at the rural area, there are some challenges for mobile coverage in those areas. The first thing is there are fewer cell towers there, which can lead to dead zones, or it can lead to weak signals. The other thing is there are some geographic barriers, like there are mountains, forests, and huge lakes that can maybe consider as a barrier. And lastly, the sparse population there is some hinders that operators usually do not like to invest in those areas because there are less people living there. And of course, there will be some consequence for people who live there, or not living there, actually working there, or maybe crossing those areas. For example, they cannot communicate with other people, and it's really important, especially during emergencies. And the other thing is it can lead to that an area won't develop and it cannot access to e-commerce. And the other thing is it's really crucial for education, healthcare, and other economic development, and also entertainment as well. The first thing to bridge the this divide is to get install more base station. But the thing is, first we have to have a look at how to measure this coverage. Usually operators measure coverage by the percentage. That means they just count that how an area of a country has access, and they divide it to the whole area, and then they can have we can have a coverage percentage. But this number usually does not provide any information about the distribution of coverage. We cannot have any idea that how this coverage distributed in a country, like what's the coverage in rural area, what's the coverage in how's the coverage in urban area. And the other thing is expanding coverage is really good, but it's usually does not happen in rural areas, and it usually happens in urban areas, which leads to the increasing this inequality. In this work, we propose a novel cellular coverage inequality index that measures the correlation between the rurality and coverage, and it can show us that the whole coverage is distributed in an area from the micro perspective to macro perspective, and how it expanded. In order to introduce this index, I will first talk about how a method to create a rurality map, and then I will discuss how to create a coverage map, and then with those information I will introduce the cellular coverage inequality index, and finally I will use Sweden as an example. And let's begin with the rurality map. Suppose this is a country, this is a fictional country. We want to create a rurality map for it. And let's say this country shaped with a certain number of points. Let's call this set A. Now we just collect the location of cities and villages with population equal and greater to a certain number. For example, in this country, we have 3 population classes, 50, 500, and 5,000. What we are interested in is the shortest distance between each of these points and the location of these cities. For example, suppose we want to measure rurality for this cross. We first look for the shortest distance to the first population classes. That means we are looking for the closest distance with the cities more than 50 people, which are all those 6 cities, which is this one. And then we go to the next classes. It's greater than 500, which are these 3 cities, and it would be this one. And lastly, we have for the 5,000. And then finally, in order to create a rurality map, we will just take an average of all these distances, and then the rurality degree of this point can be measured. If we do this process for all the points in this fictional country, then we can create a rurality map. Like you can observe, there are 3 rurality map for the 3 population classes, 50, 500, and 5,000. And if we take an average, we can have the rurality map. On the right side, you can observe the rurality map and the darkest color indicates for the least rurality, and when the color tones getting lighter, that indicates for the most rurality. And you can observe in the southwest of the country, you can see the extreme rurality, and there are also the borders between those cities are clear in these areas. And then on the second step, we will discuss about the coverage map. Usually coverage maps can be created if we suppose, for example, if the point X can receive at least 30 megabits per second of data rates, it can consider as it has coverage, and otherwise not. For example, in this fictional country, these gray circles indicates for the coverage. You can see these areas have coverage, while this white area has no coverage. And then with those map, rurality map and coverage map, we can measure the cellular coverage inequality index. In the left side, you can observe again that coverage map and rurality map. And you can observe that this in the southwest, there's extreme rurality and also there's no coverage. But how we can relate that? First, I will introduce a concentration index. The concentration index can show us the inequality and the distribution among two unrelated things. In here, like rurality and the coverage. On the axis is the proportion of online ports, and on the vertical axis the proportion of online points. We just sort each points from most rural to least rural, then we will create our concentration curve. And after that, by this formula, that means that by dividing this area includes between the line of equality and the concentration curve, we can measure concentration index. That means this curve, if this curve getting closer to line of equality, that means the fairness also increases. And once the curve overlap the line of equality, that means the fairness is totally fairness actually, and it's 0. And now let's try Sweden as an example. You can observe the rurality map for Sweden. This data is provided by SCB. Sweden, we divided Sweden into 5 population class: 200, 1,000, 3,000, 30,000, and 60,000. And then we take an average. That means now you can observe the Sweden's rurality map, and you can see these dark areas indicates for the most urban, while this yellow indicates for the most rural areas. And you can observe that when from the middle of Sweden we go to the north, the rurality increases, and there are extreme rurality in the north and northwest of Sweden. And now let's have a look at Sweden coverage map. In this figure, you can observe Sweden's coverage map for data rate of 10 megabits per second from 2013 to 2020. In 2013, you can see that most urban area of Sweden has access to the 10 megabits per second, and it increases until in 2030, almost 85% of Sweden can access to 10 megabits per second. And those areas that has no access to internet are mostly in the north and northwest of Sweden, where there's extreme rurality there. Also, in this bottom figure, you can observe the map for the 30 megabits per second. In 2030, let's say just big cities like Stockholm, Malmö, Gothenburg, and Umeå have access to 30 megabits per second, and the years go by, coverage expanded until in 2030, most of the urban areas in Sweden could access to 30 megabits per second, while rural areas cannot benefit from that. Now, we apply the CCI index for the Sweden. In this figure, on the horizontal axis, you can observe the coverage percentage, the traditional, which usually operator use from 0 to 100%. On the vertical axis, you can observe a CCI index from 0 to 1. 0 means total equality, while 1 indicates for the least. And you can observe in 2030, around 42% of the Sweden has access to 10 megabit per second, and in 2020, around 85 or 86% of Sweden benefit from 10 megabit per second. While for the 30 megabit per second, well, in 2030, only 2% of Sweden benefits from 30 megabit per second, and in 2020, roughly 18% of Sweden. But in the matter of CCI index, you can observe until 2018, the fairness started increasing. But after that, for the 10 megabit per second, the fairness also decreased. That means more urban area benefit from cellular coverage. In 30 megabit per second, again, until 2018, there was really good progress for the increasing the fairness. But after that, again, the fairness started to increase. And our desired direction would be in this direction. And the desired direction only occurs when coverage expansion happens in area with most rurality matches that of least rurality. And in conclusion, we introduce a method to create a rurality map based on distance. Then we discuss about how to create a coverage map. Then we propose CCI index. And lastly, we used Sweden as an example to measure CCI index. Thank you.
Good. Thank you, Amirreza. So, any questions? I'm looking in the Q&A right now. I don't see any questions. I can a quick question from my side, Amirreza. The coverage maps that you showed, are they so for Sweden typically, right? Those maps through the years. Are they from one operator or from several? How can you say a little bit about how you got them and where they come from, the data?
The data is provided by PTS, and it's the aggregation map from all the operators. It's not only one operator like Telia or Comviq or Telenor. It's aggregation of all the operators. That means if you just focus maybe on one operators, maybe the coverage percentage, the classical one, is not like in 2020, it won't be like 85%. Maybe the number would be, probably the number is less than that.
So if you would have access to this data from several different operators separately, this could also be used then possibly as to compare different operators, or?
Yeah, you can see what operators invest in rural area, while most operators have really good coverage in urban area like Stockholm, Gothenburg, Malmö. But when you move to rural areas, usually they're really not interested. But still people live there,
Yes.
I think they have right to benefit from cellular coverage.
Okay, good. Thanks. So if there are no other questions, I don't see anything in the Q&A, then we move on to our second speaker. Let me pick up the agenda. Yeah, the second speaker is Lindström, also from LTU. And his talk will be why ZeroTrust is needed. So I'll give the floor to you, Jon. You can share the slides if you want. Go ahead.
Okay, can you see it?
Yes, we see it nicely.
Okay, then I move on then. So yeah, I work also in the project together with other people here, and ZeroTrust is something that is not really new, but it's not applied everywhere, and I will try to get into why it might be a good thing to consider if you haven't already done that. So, as a background here, we have something which I refer to as network abstraction. Basically, you don't really know where you are in all different networks, which services you use, and how you actually got in to use those, because you might not even know that you have identified yourself and authenticated yourself. And in the future, when we have more 5 and 6G, we will probably have a lot more what we call edge services as well. And those are needed to speed up everything, basically crunch data closer to the users and have less data communicated over networks. But you have all these other types of systems. You have normal cloud services, you have IoT systems that can be more or less anywhere, common IT systems, and IoT OT systems, which is in operational technology networks or production and distribution networks like the electric grid, or if you have clean water production, for instance. And there is a rapid increase in the number of deployed IoT solutions, devices, and OT systems, and what we call as cyber physical systems that are connected. And somehow we need to manage this enormous volume and also ensure that the cybersecurity level is intact. I think we also are at the maximum of historic cyber attacks at the moment as well. So it's the world around us is not that friendly all the time. And this network abstraction, even though I am fairly conscious, I don't know all the time which service or which application and where it is. So since most of our networks that we use are interconnected. Now I have a next slide here trying to illustrate this. So if you have a common office, you might have IT environments to the leftmost, and to the rightmost you might have what we call a factory or a plant of some kind where you produce paper or energy or something like that. Then you might have IoT solutions, OT networks, and you might even have a private mobile network, 5G for instance, that you use. And then you can be connected to your subsites, basically having a private connection. To the rightmost, this orange dotted line. So you have some more IT environments or OT production sites or distribution sites. And in the middle, we have the public mobile networks, might be many of them, where you might also put IoT solutions or edge services. And to the left uppermost, you have cloud services and AI services. And you might also have your data centers or outsourcing locations as well. So as you can see, there are even more than this commonly. But it's not that easy to actually know if you sit on your cell phone to know where you are in this little mapping here. And something that many might not have realized yet, or at least a lot of providers of IoT, OT, and network equipment, is that we have a lot of new legal developments within the EU. And this will have a large impact on, in particular, the cybersecurity. And the reason for why EU has put so much on the table at the moment is the increased cost for the cyber attacks on the EU. It costs billions, and that is pretty unnecessary. If we could protect ourselves better, then we would not have unavailability, etc. in society. But for most of us, we have the GDPR and Schrems. basic to protect our personal information. And then we have the NIS2 directive. Basically, that means we need to improve the general level of cybersecurity all over EU, and in particular in networks. And this goes, of course, for almost any company from a self-preservation perspective, but in particular if you have criticality to society. And if you are part of the value chain of a critical infrastructure or critical provider, then this applies to you as well. And then you have the AI Act, which is emerging, might be applicable too. And then you have the CER, which applies to critical infrastructures like a telecom provider. You have energy, you have clean water, etc. That is critical for society. So they have additional rules. And DORA, that sounds pretty fun, but that is actually for ensuring availability and stability of financial institutions like banks, etc. And basically anyone who is a provider or sub-supplier to these, like telecom providers, also need to apply these rules. So there is a lot of things that you need to analyze. And then we have some more which relates to the equipment used, for instance, in cell phone networks or factories, etc., that communicates, and that is the RED, the Radio Equipment Directive. Basically, anything that emits radio waves of some kind need to adhere to this. And then we have something called CRA, Cyber Resilience Act, and Cybersecurity Acts. And this goes mainly for providers of equipment and systems. So if they basically are in the value chain of critical infrastructures, they need to have quite a bit of security as part of that. The marine business is ahead of the land-based, and they have already made a de facto industrial standard. So if you're interested, you can take a look at the marine business, and it's very likely that the land-based will have something similar. You have some more things that applies to if you have factories, hospitals, etc. And for once, it seems actually like the EU cyber regulations and directives are actually ahead of reality. Usually it's 20 years behind, but now due to the cyber attacks, it's actually ahead. So this is an interesting situation. I don't think we have ever had the situation like this before, actually. So some people call it a compliance nightmare because they have so many new requirements to catch up with. And some of the things that come out of this from the EU is concepts for cybersecurity, and that is called, these are not new, but they are actually getting implemented and requested now. And that is privacy by design. Basically, a system should have privacy when it's built. Then you have security or secure by design. Basically, it should have all security capabilities from start. And secure by default. That sounds similar, but it actually means that it's configured and set up so that it's secure when it's actually commissioned and getting started to be used. So it's almost the same, but not really the same. And then you have the principle of least privilege, and that basically means you should be able to do as little as possible that you need to do, and not as much as possible. So that is basically to minimize potential mistakes and overuse. And all out of this, we have the need for zero trust, and I will get into what that means in a few seconds. As you can see, there is a lot happening, but there are still some important stuff missing, and that is normative standards. Basically, the law says what you need to do, but not how you should do it. So we need that. So that is a big problem at the moment. And I think there is, from my view, a lot of lobbying going on so that the standards should be reasonable, or perhaps too reasonable in my view anyway. So And to sum this up a little bit, so that if you look at 6G, the cybersecurity in 6G will evolve from 5G, but additional things will be added. And this is to prevent large-scale attacks and ensure network availability. And we have a lot of things going on. It doesn't matter if it's on the internet or if it's in the mobile networks. The mobile networks might have a little bit higher protection level, but it's still moving a lot of things in there anyway. So what we've done so far in this project is that we have mapped out some challenges and security concerns in 6G. And to start to explain what ZeroTrust is. So basically, when you move from one network or a subpart, a segment or a zone in that network to another, and the security level or security requirements are not the same, we think that the user should always, I mean always, be firstly identified and then authenticated. That means basically you have to prove who you are, basically like using a bank ID certificate or some kind of other app or whatever you have, or a password. And then you get access and authorization grants, basically what you can do granted. And ZeroTrust should apply to not only users, but administrators on networks, applications and services always, as well as those who actually manage the networks. So it's not just for the users, it's actually for those professionals who are behind the scenes as well. And the ZeroTrust concept means you never trust anyone, you always verify who they are. And you can do this manually, or if possible, also you make it automatically. And then you might not have to log in all the time, but then you need to have some kind of solution doing that for you. And some examples, if you go to the leftmost bottom, you have two networks that have the same security levels and security rules. And basically, it could be a green light to move on, but I think you should move up a red light there so that when you move over, you actually have to verify who it is that is moving over. It's better. And if you can automatize this, it's not that big of a hassle either. And in the middle, you have a green network moving to a yellow. Yellow means higher level, higher security level. Then it should be identification, authentication. And the same is if you come from a network with a higher level to a lower level, then you should also do it. So basically, it's a great thing to always do this. And here is a lot of things. But in order to achieve ZeroTrust, basically, you need some kind of way to identify and also authenticate the users. And that is sometimes called IAM, Identity and Access Management. And you can have quite simplistic ways of doing it, basically passwords, moving up the ladder to actually combine and automatize this. And I think that if you have really high security requirements, that you should have some kind of two-factor or multi-factor authentication that could be combined with behavior metrics. And that means basically how you type on your keyboard or how you move your mouse, etc., so that it can be recognized for each user. But that requires that actually you have been using your security solution for a while. And who can access or do what, how and from where? We need to have some kind of life cycle management so that we don't have old user accounts, old users that are not supposed to be in the systems. We update the access rights and authorization levels. Basically, if you move from one rule to another in a company or you leave, then that should be basically almost instantly changed. And if you look at different levels of access and authorization, if you're in a company, for instance, it's quite common that you have very simplistic user/operator. That is a rule. Basically, you're using a system of some kind. Then you can have a local admin that can actually do some things on the local system, and then you can have a higher level admin or super user or super admin or something like that. That is a fairly common. You have 3 or 4 levels. So basically, if you would go upwards from a user towards an admin, that is okay. So then you can log, in my opinion anyway, you can log upwards. But if you go the other way around, basically if you're a super user or something like that and want to go down to a user operator, you should be required to log out, because if you're a hacker, otherwise you could access anything if you don't, or if you're not required to log out. So going up is okay, going down is not okay. That could be worth to remember anyway. That's a good principle to use. And further, if you have large networks, it might be a good idea basically to divide them up into smaller pieces. Because if somebody comes in, they will not get everywhere. And another thing is that we need to harden the networks, the servers and everything we use, basically even the cell phones, so that they are not like Swiss cheese. They have a lot of holes in them. So we need to have Swedish cheese instead, which have no holes. And that means basically taking away everything that is not needed, and then you plug everything that is not necessary, like open ports. You take away services. You might do other things as well. That is what we call hardening. Further, we need to check what is going on and see if there are any threats happening. And now and then actually make risk assessments or risk analysis, basically to find out new problems as the world evolves. And we need some kind of policy and policy enforcement, because we need to make some rules. And if we have an infrastructure, so that is actually enforced everywhere. It could be for your internal IT network or your internal corporate network, if going out to cloud services, etc. So what we propose is that we have a ZeroTrust architecture stack in the middle, enforcing policy. And a publication to check if you're interested further in this is Nurun Nahar's EAL's survey on ZeroTrust architecture. Okay, so my final words are: be proactive and not reactive. So secure your assets and your network, etc. And that is a lot better to be proactive than reactive when something happened already. So, okay, Jaap, I'm complete now, unless there are any questions. So.
Excellent, thank you, John. I don't think there is any questions in the Q&A. Quick question, very, very short. Just you talked about these normative standards.
Yes, I can move back to that.
Is there now in relation to 6G? Is that part already? Is that on the table of 3GPP, or where is this? Which organizations are likely to create those standards?
I think for the mobile world, 3GPP is probably working on this as well. But then you have the EU Parliament, that is actually those who will say which is the normative standard. So I think there is a symbiosis in between a lot of organizations, because it has to be reasonable and accurate, and that is not that easy basically for lawmakers to understand all the time. And then it's also a lot of work to do this, so that perhaps it should be in different steps, so that you don't get the big shebang at once, because that might be a little bit problematic if you have a hard enforcement date, basically. So I think that you might have it in a few steps, but we need some kind of normative standards, basically, since it's so many areas. If we just say what to do and not how to do it, it will be very complicated for a lot of, especially companies without a lot of legal people as well. So.
Yeah. Okay, good. Thank you. So let's move on. Our third speaker is, we're moving to the US now. Harri Saarnisaari from Oulu is there with us, and he's going to talk about Starlink experiences. So Harri, go ahead.
Yes. So I think you see my slides.
Yes, we do.
Okay.
Excellent.
Okay. I will talk about Starlink measurements, what we have done in last 2 years. Okay. So why we are interested on Starlink? So 6G will most probably include non-terrestrial network element, and it's very important in remote and rural areas where the mobile network operators are not providing enough capacity. In northern Finland, Sweden, Norway, and other parts of the world. In Canada, it's very often used in remote villages. Almost every house has Starlink receiver. And we also want to know how it works, in which situation it works well, and so on. And that's why we are doing these measurements. And in 6G, you know, in 5G, the NTN was a latecomer, so the signal is not optimized for satellite usage. So maybe in 6G they could do, or we could do something better and propose optimized waveform for satellite usage. So it's important to know how Starlink is built. Information is not very well available, but you can get some information by reading various documents and websites, because these parameters help you to understand the link budgets and so on, what is needed. And for example, if we use these Starlink parameters and calculate the link budgets for the Starlink receiver, we can then better understand how the direct UE access link budgets are, where the antenna gains are much smaller. What is the potential capacity for direct user access? And here we have this information, what we have found so far from the system. So the orbit height is something like 550 kilometers, 600 kilometers. They are using different frequencies. So KU band, so it's about 10 gigahertz downlink and 14 gigahertz uplink, and then KA band, which is 2 times higher, about 18 downlink and 30 gigahertz uplink. The problem is that then in the Starlink receiver, you don't know which band it is using, so you have to guess what is happening there. Then the waveform is, of course, proprietary waveform, like always in satellites. Maybe NTN, new radio waveform, when they appear, then we know what the signal is, but not in the Starlink case. But we know something, so subcarrier spacing is 200, so it's OFDM signal, 240 kilohertz subcarrier spacing, so that it can tolerate very large Doppler shifts. There are 1024 subcarriers, so that the total bandwidth is something like 240 megahertz. But for me, this sounds like this is 5G new radio signals with the largest subcarrier spacing. So they have not been very innovative. Okay, maybe the innovation part there is then how the data is put in the subcarriers and how the control data is done and so on. Modulation in Ku band downlink, it's QPSK, and uplink, where the transmit power is less, is PPSK. And Ka band, they have these two plus then 8 PSK and 16 APSK, which are often used in satellite communication. And for the power, we see that we saw IERP values that are 32 dB watts per whole bandwidth. So it's over 1000 watts what they are transmitting, very high powers. And then the total bandwidth reserved for the Starlink, it's 8 times this 250 megahertz. So there could be 8 different channels in one satellite. The satellite Starlink system, what we have is shown in this figure. This is the receiver antenna. So it's about 57 times 51 centimeter antenna array. It's phased antenna array which tracks the satellites. In addition to this antenna, there is power source and Wi-Fi router. So you get the Starlink network by this Wi-Fi router. Then they have a different kind of service plans, and one is for fixed position, which is the cheapest one. We have this roam so that we can move to different places, and then there are some others. Now if you take this antenna there and its dimensions and the wavelength, then you can estimate that there are something like 1000 antenna elements, or there could be 1000 antenna elements in this array. So 30 dB array gain in this system. But I don't know have these elements 0 dB I gain or 10 dB I gain, or what they have. And is this full antenna table used for 10 gigahertz band, or only half of it, or how it's done? It's open to me. Then with the system there is this Starlink app. So you upload it into your phone, and you can see different kind of statistics using that app. And then you can run also speed test provided by the Starlink using that app, and so on. And then the start of the system is automatic. You switch the power on and it starts operate. But when you shut it down, you have to use this app to switch it off. And our goals are to check how well this Starlink is working in rural and remote areas in a bit different conditions. I will show the figures later. So what I mean by this. And we try to see if the data rate is enough for various applications, and what are the problems with the systems, and probably with the other satellite systems then too. And then we want to somehow publish these results so that the public will see that how they can use this Starlink system. Measurements, when we started, we didn't know much about the Starlink systems. So one surprise was that even though there are several thousand satellites, there are very few in the north. You can see it in these figures that there are a lot of satellites in over Central Europe, but only 2 or 3 over Finland, Sweden, and Norway. Still we have connectivity here, but if we would have thousands of users, then I think the capacity would be limited. But so far users are very few. we didn't have idea how fast it connects, and based on the test what we have done in different places, if you have very good visibility to the sky, it's just few minutes, so quite fasting. If you are in bad place, then it could be over 10 minutes, and usually we observe that if it's more than 15 minutes, then it's better to stop and find a better place. It will not connect. But then if you are at the same place and restart the system, then the connection is very fast, just few minutes or even less. Yeah. Then our purpose was to measure Starlink in East Finland, and then we had a big surprise that it's not working there. So if you go very close to the Russian border, it does not work because they have cut the service in Russia, and some beams cover both Finland and Sweden, Russia, and those beams are then shut down, and we cannot use the Starlink in the Finland. I'm not sure if the situation has changed, so have they redirected the beams so that it will work closer to the Russian border right now. Where we did measurements, these first measurements were done here in the bottom circle there, which is east part of Finland, so Puolanka and Suomussalmi area. And then second measurements were done in northeast part, this Inari and Sevettijärvi area. And lately, few months ago, in Pöyrisjärvi wilderness area with the reindeer herders. So in different parts of Finland. So this shows the few places where we put the antenna. So we went to these forest roads and put the antenna there, and we put it in the open places and little forested areas like in these figures. So there are trees between the antenna and space, but still it works very well. So no problems. But if you put a building or hill, then it does not work. And I guess that if the forest is much more dense than these, like spruce trees and so on, then it does not work, or at least so well. And here are some results from the Starlink app. So there is this, it shows you Starlink speed and Wi-Fi speeds. So you can see it's over 100 megabits already last year. I think in best we had nearly 200 megabits per second in some places. We of course did also run some internet speed tests. This red line, so red arrow shows the pair, and this shows that it's matching quite well. The Starlink, what Starlink claims and what the speed test tells you. Then in Inari area where we were in winter time, so the speed was there even a bit higher. It was few months later than these first measurements, so maybe they had improved service rates. And then in this Pöyrisjärvi area, it's really wilderness. There is no electricity grid or nothing. We use these six-wheel drivers to go there. We had to be very careful how to transport this antenna so that it does not break in these very bumpy roads, but it survived both ways, so that's good. And here in this is reindeer herder's cottage where we were testing it with the diesel generator, and this cottage is in the slope. So this leftmost figure with the vehicle, that is in the middle of that slope. So where I took the picture, the slope continues, and that caused us some problems. So first the antenna was very close to the cottage. There was quite good visibility to sky, but still when the correct direction of the antenna was then behind the cottage, so that it blocked it totally, so it didn't connect at all. Then I removed it by something like 10 meters and it started working and gave us some results. And then later on we put it in the top of the slope and it provided something like 50 megabits more data rate. So the place selection has big impact on the data rates. You have to know how to use, and maybe this is then part of the things what you have to tell to public. So where to place the antenna so that it works the best. And the app has now new features like this obstruction map. You can see on the right. So there is these red dots are where it sees some problems, and actually these were these trees behind the antenna in this leftmost figure. But you need lots of time to collect this information. I think this obstruction map was done after 5 hours of usage. Then with this new version of the app, you can do ping test there, and you can see that over 99% of tests were successful. Latency in our measurements was something like 74 milliseconds. Largest latency was over 100 milliseconds. So not bad. And what we plan to do next? So far we have used the Starlink own test statistics, but it's company owned statistics, so we are not. Can we be 100 rely on it 100% or not? And our aim is to confirm these results by using other tools. So we have Cosium tool, what we plan to use, and iPerf tool also. They both do similar kind of measurements, but this Cosium is more capable. And we want to do same test what they are showing there. So throughput, the number and duration of connection breaks, latency, and so on. I think this ends my presentation. Are there any questions?
Thanks, Harri. I'm looking in the Q&A. There are no questions. I have one very quick question. We don't have much time now, but did you mentioned about the capacity as well in the beginning, that may become a factor later on. Can you already say something about? I mean, you were pretty much alone, perhaps, using this in these regions, right?
Yeah.
Do you expect the performance to decrease once more people are going to use it?
Yeah. Okay. But I'm not sure where the limit is, but
no. But it's nothing you could measure.
Given the data rate, and if they have 8 channels. 8 channels, so it's a lot of capacity. 8 times 200 megabits, so it's over gigabits of capacity.
Yeah. Okay.
So
good. And one more question now.
Users, yes.
One other question in the Q&A. Did you test it under mobility conditions, or is it mostly static?
It was static, so we don't have this mobile version, so you cannot drive with this antenna. We plan to have it, but it's not yet in our hands. Yeah.
Okay, thanks a lot, Harri. We are moving on in the agenda. We have two more talks. The next talk is by Martti Ahvenjärvi from Lapland University of Applied Sciences, and he will talk about the preliminary results of connectivity needs in remote and rural areas. So, Martti, the floor is yours.
Yes, thank you. Hello, everybody. My name is Martti Ahvenjärvi, and I am here presenting on behalf of Lapland University of Applied Science, a partner in the Arctic 6G project, some of our preliminary results and findings under the topic of connectivity needs in remote and rural areas. I'm currently a student in the master's degree program in digital business management, and I'm writing my master's thesis on this topic using the data gathered in this project as part of my research. And our principal lecturer, Tanja Suomalainen, is also part of the project group, and she has helped out to put this presentation together and is supervising my thesis work. The content of the presentation will be as follows. First, I'll quickly go through the background and the Lapland UAS focus on this Arctic 6G project. Then I'll take a moment to talk about the questionnaire, the Arctic 6G survey that the Lapland UAS conducted. And in the third part, I'll make a couple of highlights, raise some topics from the collected data, and check what we can deduce from those answers. And finally, some conclusions and things to consider as we move forwards with the surveys or my thesis work and whatnot. So in the Arctic 6G project, the Lapland UAS has focused on identifying challenges the end users are facing with the current connectivity technologies and to create an understanding of their connectivity needs in rural and remote areas. In order to keep the Arctic area viable for businesses, these findings, well, we hope that they would guide the development and implementation of the 6G technologies. In my thesis, I'm further putting emphasis on what needs the companies and businesses have for the next generation technologies from the business development and digitalization point of view. The survey, the questionnaire, as a part of this Arctic 6G project, it was aimed to promote the development of these new mobile network technologies in the Arctic region, give the people information that there are new stuff coming at some point, and also to map out the respondents' perception of the current state of the mobile networks and the potential needs and what the more advanced networks should provide in the Arctic area. And we hope to see that this survey might offer some points of thought for the whoever is building these networks and planning out the implementation of this technology. The questionnaire itself, it was on a web-based platform with a quite wide array of multiple choice, scale, and open-ended questions. The survey was available for the first half of this year, and it was promoted in social media and in events, and it was shared directly to over 1,300 emails. All in all, we received 148 responses from rather diverse demography of respondents. All regions age groups, work-life situations, from entrepreneurs to business owners and employees and students. Everything was covered in the answers quite well. Now moving on to some of the results. A lot of this will link quite nicely with what Amirreza presented in the beginning, and also maybe some points for Harri's presentation also. This is not by no means a complete rundown of all the results and answers, but I'll highlight some of the questions and answers where we can see some clear similarities or differences amongst the different groups of respondents. In the first few slides, we have everything grouped together. There's only one group of respondents, which was like all the people. Well, rather not so surprising, 99% of all the respondents find that internet is very important or important in their daily life. Also, consistently working internet connection, it was also equally important. Well, this question highlights the necessity of reliable internet connection and infrastructure across all the different regions, regardless if the respondent was living in a bigger city where the connections are good or in the sparsely populated areas. It's only very small part of the respondents, the 5%, think that the internet availability is only slightly important and not important at all. No one thought like that. Significant majority, like 95% of respondents, have noticed a clear difference in internet connectivity between the populated areas and then moving to the more remote regions. I guess this again is not a big surprise when we are talking about the Arctic region. The distances are long. People live in different places. They have to move long distances, and moving from one central hub to another, you are probably facing some connectivity issues. But this again highlights that these are things that that area is suffering, and it affects everybody in the area. Addressing these issues could significantly enhance the quality of life and support the daily activities and well-being of the residents, and even enable the economic growth opportunities in this Arctic region. The respondents were asked to rate their current internet connections quality. It was for their main residential area, and 59% rated their connection to be good or excellent, and 41% rated their connection to be fair or worse. And these are now two groups that I will be using in the upcoming slides to show some differences in their responses. Blue color will be for the good group, and an orange color will be for the respondents that said that their connection is fair or worse. Although Arctic 6G is a project about next generation mobile networks, and the 4G and 5G mobile connections were amongst the most used in both groups, we can see that when asked about the connection types, the fiber optic was more present in the group who perceived their connection to be good. Fiber optic is maybe rather new technology for consumers, and at the moment, at least here in Finland, there seems to be a huge boom. Companies are building a lot of new fiber optics, and although at the moment the fiber optic seems to be quite reliable source for good internet connections locally, it doesn't solve the issues and needs for reliable mobile connectivity outside the main cities. From regional point of view, the connectivity quality was generally perceived to be better around the larger cities. Most notably, the bad connections were reported from the eastern Lapland area and then from the northern Sweden area, which was mostly coming from the companies or respondents that were part of the reindeer husbandry businesses. The other regions consisted the northern east part of Finland and the eastern border part of the Finland. Then we tried to understand how respondents feel about their current situation. We asked if users have felt concern due to poor internet connectivity, and the majority of the respondents, 64% from those with good connections and 98% of those with bad, indeed expressed their feeling of concern. Out of the 24 more in-depth clarifying answers that were given, most of the concerns were related to the availability and connectivity. Only 2 answers mentioned the speed of the connection to be a source of concern. And these are some of the answers, and I guess these highlight the critical need for improvement and reliability of the internet connection across the various aspects of daily life, from travel and business to emergency situations and outdoor activities and all that. Unreliable internet connections are causing delays and operational challenges for businesses. Connectivity issues are raising serious concerns about reliability of the emergency services and the ability to get and send help during critical situations. And people feel that, these are important things. Addressing these issues is essential for enhancing the safety and overall quality of life in these regions that are affected. 2 business sectors most affected by the poor connections were reported by respondents working on the areas of tourism and the reindeer husbandry. These are businesses that are not tied to one location. They are mobile businesses, so they need to rely on the mobile connectivity. The tourism sector also is highly seasonal. The need for the capacity and the type of connectivity fluctuates. For example, while the hotel can operate on fixed lines, then if they organize a snowmobile safari or something, they require the mobile connections. Then we asked businesses to rate their level of digitalization, how it is evident in their strategy and operations. Do the businesses use digital customer interfaces, and how much digitalization is in their internal processes? And from the answers, we can see that the companies that reported poor internet connections scored themselves lower in every category. Businesses suffering from poor connection are maybe not willing or able to increase their digitalization levels, and they don't necessarily see how they could do it and at the same time control the risk of not having the digital services available for them all the time. Then we asked how businesses plan for further developing their digitalization and what benefits would they see from faster or better internet connections, and how would they want the connections to be developed in their area. 25% of the answers were directly wishing for a working connection. It didn't really matter if the current connection was perceived good or bad. Even the businesses reporting good connections saw the value in having more reliable and better coverage and working connections throughout the whole region. Poor and unreliable connections were seen as the single most limiting factor for businesses like development and adopting new digital technologies. Again, only 3% of the answers were expressing some form of need to have a connection speed increased. So, as a conclusion, the connectivity issues were seen as the number one reason for frustration and hindrance for developing the businesses in the areas suffering from poor mobile coverage. There was some dismay on ongoing dismantling of the 3G networks and not having equal coverage in the 4G and 5G. Speed is irrelevant if there is no connection. The practical needs are different from the technological advancements previous mobile networks generations have promised. Solutions developed for densely populated areas are not directly applicable in the remote and rural areas, and the needs of these regions should be taken in consideration when planning out new networks and technologies. And thank you. This concludes my presentation. I will leave you with the details for our principal lecturer, Tanja Suomalainen. You can contact her if you have further questions regarding the survey itself or Lapland USA involvement in the project. Thank you.
Great. Thank you, Martti. So there are no further questions I see now here. Do you know anything about the geographical spread, the geographical distribution of the respondents? You had 150 respondents almost. Are they all in rural regions, or do you know anything about it?
Yeah, we have the rough idea. Was it this one?
Yeah.
This spread.
Yeah. Okay. Okay. That's yes. Okay. Yeah. Yes.
But we didn't go into more detail about this.
Yes. Okay. Okay. Thank you very much.
There's another question in the Q&A.
Okay, I'm reading here. Have the results been presented in, for instance, a NATO discussion? Things of dual use so whether these results have been discussed in a NATO context, I guess.
I can answer this. No, we have not discussed so far.
Okay. Okay. We move on to our last speaker, Faryal Junaid, and we will dive into the topic of metasurfaces to enhance coverage. Faryal is also with LTU. So Faryal, open your mic and please go ahead.
Hello, everyone. Let me share my screen.
Yes, we see it nicely. You have to put it in presenters mode.
Okay. Hello, everyone. Today I'm here to present our work on REIS-assisted coverage enhancement in an urban setting. And I present this work under the supervision of my advisors, Jaap, Ricard, and Chandan. And this work was done together with ZE, who is now with Ericsson. So as we can see in the figure, in 6G networks, we are moving to higher frequencies than in the previous standards like 4G or even 5G. These higher frequencies, such as millimeter wave and beyond, offer significantly more bandwidth, which is excellent for data rates, but introduce a major challenge, which is signal propagation, because as we experienced in lower frequencies like in 4G and 5G, the signals can bend around the obstacles, as we can see, as we would have seen in the case of 4G or 5G. But this is not the case in 6G networks because of the higher frequencies. The signal is more sensitive to physical obstacles. So even bad weather or buildings or trees can weaken or block the signal, which can create coverage gaps and reduce reliability in urban environments. Here the objective is to evaluate coverage and throughput performance in such scenarios. And the solution provided is a reconfigurable intelligent surface, which I'll be coming to explain a little bit more. But in this figure, we can see that we have a base station which has maintained a direct path with some of the users or devices, but it has a blocked path in case of a 6G network to most of the users in the blind spots. So the motivation behind this work, if we focus on a vehicle to everything communication in a dense urban environment, which is going to be a critical aspect of 6G networks. So where the vehicles maintain communication between the devices and the base station. In a V2X context, the base station allocates resources to a wide range of sensor devices that support vehicle safety and efficiency. For example, a vehicle's onboard sensor may receive real-time weather updates from the base station to adjust driving conditions safely. And similarly, vehicles can receive traffic congestion updates to optimize route planning. So in these scenarios, we can see that a coverage gap can lead to a potential hazard. And we have to maintain a seamless connection between the devices and the base station. In this scenario, a reconfigurable intelligent surface can enhance communication by reflecting and modifying signal paths. So what is a reconfigurable intelligent surface? We will call it a REIS from now on because we have short time. And in literature also, the term adopted for the short term adopted for reconfigurable intelligent surface is a REIS. As we can see in the top right figure, a REIS is a planar surface. We can see the visual representation here. It is a planar surface that consists of passive reflective elements. And we can see in the bottom left figure that each of these elements is controlled by a tunable circuit, which can modify the phase or even polarization of the incident signal. In this way, the REIS can redirect signals towards targeted areas, enhancing coverage and signal strength. This adaptive mechanism allows REIS to operate in real time with minimal energy, making it particularly valuable for dense urban environment settings, where traditional signal paths are often blocked or hindered or may result in weaker signal strength. the applications that I have already mentioned are 6G networks in Internet of Things, vehicle to everything communication, vehicle to vehicle communication. So the applications are very vast. But of course, the REIS also comes up with its own set of challenges, and the biggest challenge is the need for perfect channel state information to accurately adjust the phase shifts of each REIS element. When we talk about theory, if a REIS could obtain continuous and precise CSI, which is done through a link, consistent physical link between the base station and the REIS. In theory, if a REIS could obtain that, it could optimally reflect signals toward targeted receivers, maximizing signal strength and coverage. However, in practice, acquiring and updating this information in real time it is complex, it is resource intensive and often impractical as well, especially in dynamic and high mobility scenarios like V2X communication. So a challenge would be to simplify the protocol of the beamforming protocol of the or the reflection protocol of the REIS. It is also crucial for industry adoption because the industry is a little skeptical about the implementation and deployment of the REISs in the 6G standardization. I will explain a little about the system model here. We can see that now when we have come from the last figure to this one, with the deployment of the REISs are shown in the red. These are planar surfaces with multiple elements, and they can be, deployed in, on the facades of the buildings or as billboards. They can be deployed anywhere. The feasibility is very simple. But as soon as the deployment is fixed, we can see the reflections going around the blind spots, and we can see that we have coverage. In this system model, we have a single antenna base station. We have multiple single antenna users, and in our case, to maintain the symmetry of the map, which is a crossroad in a dense urban environment, we have deployed 3 REISs. The objective is to improve coverage and throughput using an autonomous REIS reconfiguration protocol. So, autonomous REIS presents a solution to the challenge of acquiring a CSI and obtaining and maintaining a link between the base station and the REIS by operating without real-time channel feedback. So instead of relying on CSI acquisition, an autonomous REIS uses pre-programmed phase configurations, or we would like to call that a code book, which is pre-programmed, and it sequentially and efficiently directs signals to cover specific areas corresponding to a specific geometrical angle. This approach allows for consistent and low-cost coverage enhancement without the need for a dedicated control link between the base station and the REIS. This setup makes the REIS highly practical and scalable because we can deploy as much autonomous REISs as much we can, depending on the ergonomics and economics of the system. And this is particularly feasible in urban applications where CSI acquisition would otherwise be a limiting factor. To visualize the function or the configuration protocol of the REIS a little bit more better, we can imagine a lighthouse on the sea, which casts its beam of light in a specific direction, illuminating only the segments of the cast one at a time as it rotates through the hemisphere. So an autonomous REES also operates similarly in a sequential reflection mode. So it reflects its beam one at a time in a targeted area, enhancing SNR in that particular area. And this sequential operation ensures that each area where the beam is focused by, or the reflected beam is focused by the REES, uh, uh, we enhance communication accuracy and efficiency, much like how the lighthouse guides ships to navigate safely by illuminating only the required segments of the sea. In both cases, the lighthouse and the REES, it's a very strategic and a controlled process where we deliver signals or lights to key locations at precise intervals. It is crucial to highlight that there is no feedback link between the base station and the REES in the case of an autonomously functioning REES. Sorry. I will explain briefly about the channel model. We can see that we have a single antenna base station, and we have simulated a Riccian fading cascading channel that simulates blocked or direct paths to between the nodes. With an autonomous REES protocol, we use pre-programmed codebooks for sequential signal reflection, and the known parameters in this case are the distance and the geometrical angles between between the base station and the REESes. And we don't know about the true location of the user or the receiver, and we don't require that information because the autonomous REES directs its beam towards the entire map area and gets as a feedback the SNR at the base station. And on the basis of that, the base station the base station can make the decision about the scheduling algorithm, the scheduling decision. The objective here is to evaluate coverage and throughput after scheduling, and the scheduling algorithm that we have adopted is proportional fair scheduling, which is conventional. The simulation operates at 3 gigahertz carrier frequency with 3 REESes, and we have assumed that each REES consists of 201 elements. So roughly speaking, the size of each REES is in the order of a meter squared, or it is less than a meter squared. We have a uniform and random user distribution in urban crossroads, and there are 50 users per channel realization. We evaluate our work through the CDF of user throughput and also the coverage heat maps. The comparison scenarios are where one is where we have no REES deployment, the second one, which is the proposed autonomous REES, and the third one is the coherent beam-forming REES, where the factor that the CSI has to be acquired consistently and without any break. The REES acquires that information about the channel state information and redirects the signals at the true location of the user. So here we can in the bottom we can see that in the bottom row we can see the CDF empirical CDF of the autonomous and no REES and also the coherent REES scenario. The blue curve shows the scenario where we have no REES deployment, and we can see that in this case, more than 40% of the users are starved. They don't have any coverage, and this is also evident in the heat map here. But as soon as we can see from the red curve, as soon as there is an autonomous REIS deployed, we can see that all the users have coverage and no user is starved, but at the cost of the best users throughput. We can see that the best users sacrifice some of their data rate or efficiency so that the worst channel condition users may thrive. And this is owing to the scheduling algorithm that is the proportional fair scheduler. But the deployment of the REIS enables the scheduler to strike that balance between the users and the throughput and the fairness. The third one is the benchmark performance, where the true location of the users is known. And we can see that the autonomous REIS strikes a very low cost and efficient balance between no REIS and real-time reconfigured REIS scenario. I will conclude my presentation with the takeaways. We have shown that coverage enhancement in 6G networks is a key challenge, and it can be, there is a solution to it by deploying a REIS, which is a low-cost solution, and we can further simplify its reconfiguration protocol by eliminating the need to maintain a consistent feedback link between the base station and the REIS, and eliminate the real-time adjustments. And with this low-cost solution, coverage enhancement is still possible, and it is very feasible for industrial adaptation as well. Thank you very much, and I'll be glad to answer any questions.
Great, Faryal. Thank you very much. I'm looking in the Q&A. Let me see. There are no questions yet. One question.
There is one question
there
from
is one
Mikael
question.
about reflecting surfaces.
Okay, do I miss it? I have to scroll up. Yes. So the question is whether if you have these kind of reflective surfaces in the city environment, are city planning and architects, are they already in the loop, let's say? Are they aware of the need, or yeah?
That's a very relevant question. I would say that after the standardization, it is something that they are going to be in the loop, and they are going to be very much a part of it. That because then the engineers and the smart city developers, they need to work in collaboration to deploy the REISs in the best positioned way, so that the performance is guaranteed, the performance increase is guaranteed. But for now, I'm not sure.
Okay, good. Thanks. I'm looking at the clock. It's already past 3:30. So thank you again, Faryal, for your presentation. I'm going to wrap it up. We're a bit over time, but I think we have heard quite a broad spectrum of different presentations and topics. I want to again thank the 5 speakers and to you all in the audience for attending. And with that, I close this session. Thank you very much, and bye-bye.